All right, well, let's just give it a little, I just pass around here. Very cool. Well, they survived crashing into the ground, so I can at least know where transmitter did. So, my name is George, N3VQW. Most of you know me, but for people who may be watching this that don't know me, I'm just introducing myself. So today I'm presenting on combining amateur radio with the model rocketry. A couple of years ago, I got the model rocketry bug and I lost the rocket. It was a cheap $17 rocket, but I was like, man, that kind of stinks. It would be nice to be able to have the rocket send me where it is. And, me being a ham, thought, well, maybe I could put a transmitter on board and transmit data. And I'm starting small, and I'm planning to increase the complexity levels as I go along. Yeah. Why combine ham radio with model rocketry? Like I mentioned, real-time telemetry during the flight. Monitor key flight parameters such as altitude, its location, and what status of flight. So you can have it say, hey, I just reached out at you. Hey, I just deployed a parachute. Hey, I'm on my way down. I'm 100 feet from the ground. I've landed. It also creates the integration poses technical challenges that foster creativity. You be inventive. How do I install a radio module in my rocket? How do I, build the mounting frames? How do I protect the radio from impact? Creates a collaborative environment between two passionate technical communities, ham radio and model rocketry. When I showed up to the rocket launch with my rocket and YOG antenna, let's just say some people got excited and they were willing to help out. I'll record the video for you. This is really neat little experiment. So, technical. So the radio modules I chose to use were Adafruit Feather N0 RFM69CHW. I have no idea what the acronym means, but it's what it is. And it's a packet radio, so it's designed to send digital packets of information. The radio module itself has 100 milliwatts of transmit power. It's Arduino compatible, so it's basically an Arduino board with a 433 megahertz radio on it. You program it using Arduino IDE. So if you're familiar with Arduinos, you use the same tools and libraries basically as you would on that environment. It has easy to access libraries and sample code. As I mentioned, this module transmits on 433 megahertz, which is the 70 centimeter amateur radio band. Using the amateur radio band also allows you to avoid interference from commercial rocket telemetry or other control systems that people may be using because they use remote control rocket launchers. Some people might have their commercial telemetry and tracking systems that could interfere with other rockets. So chances are they're not using the ham bands. On the rocket, I paired the Adafruit Feather N0 with an Adafruit BMP390 barometric sensor. Oh, by the way, the radio modules are $25 a piece. Cheap. And the BMP sensor is like 12 bucks. So the BMP sensor measures temperature, altitude, and pressure, and drives the altitude from the barometric pressure, basically. And it does it at sea level. So it knows how high you are from sea level. I built a custom balsa wood frame to protect the radio module because, hard landings, etc. Plus, I don't want the parts floating around inside the rocket. Suddenly goes from 0 to 200 in a few seconds. Needs to be held in place, and then the shock of the deployment and landing could potentially damage your radio. So I built a little balsa wood frame that goes inside the payload. That worked really well. We'll get to that. And I modified an existing rocket for my fleet. I have approximately 80 to 90 rockets. I lost count. And I have 2 of them that had an adequate size payload section. So, anyways, programming. As I mentioned, the programming is done through the Arduino IDE. I started off with the Hello World program. And you just install the libraries, go to example code, select your radio module, they have 2 of them, one for receive, one for transmit. I removed the encryption code. By default, these modules, the sample code will encrypt. And as you all know, it is not legal to use encryption on amateur radio frequencies. In Europe and Asia, you don't need a license for that band, and encryption is allowed. So by default, the sample code has encryption enabled. I added the BMP sensor code after figuring out how to work with that. I added calculations to calculate the altitude from the ground, because remember, the sensor is giving you altitude from sea level. And basically, I get a reading first and say that's going to be the ground level, and then all subsequent readings after that is just a basic subtraction. I did discover a transmitter, sensor startup instability. The first readings are absolute garbage, which, if you're reading the first reading saying this is ground level, it's just going to give you some really, really weird numbers for your altitude, like in the negatives. Obviously, if a rocket's negative 3,000 feet, it's in many, many pieces. I modified the data to transmit in CSV format instead of saying this is the temperature, this is the altitude, this is the pressure, this is the battery level. I had it spread out in the CSV format, common separated value. That way, on the receiver side, I'm just having to spit into a CSV file as it receives data. Makes it easy to import in Excel or whatever tool you're going to use to aggregate the data. And one of the last things I did was, while I was reviewing my code, I realized the function that blinks the LED, which is just a visual representation of that the module is actually running, was taking 150 milliseconds to run. So every time the LED does this blink cycle, you're not transmitting data. That's like 13 to 20 packets that you're not transmitting. It's a significant loss of information, in my opinion. So I rewrote the code so that instead of having a delay to turn the LED on and off, I just had a counter. So every 25 loops, it either turns the LED on or off. LED on, LED set equals 1. Next time it sets it to 0, turns the LED off. So it doesn't use any cycles to that is not transmitting. So it's more efficient. On the receiver module, it has basically the same setup as the transmit, except it has receive code. It's much simpler. And the only thing I'm doing with the receive is once it gets a packet, it spits it out to the serial port. That's it. So obviously, I also removed the encryption because without the transmitter encrypting, you're not expecting encryption on the receive side.
Transmitters in the rocket, the receivers on the ground.
Yep. In fact, the receiver, in this case, is taped to the antenna. And the reason why it's taped is so it doesn't move around. There's a really tiny microscopic UFL connector that I hand soldered on using a microscope and tweezers. And I didn't want to break, so everything's taped down so it doesn't move around, break off. So that's I call that my yogging on a stick. And the stick is actually one of my rocket painting sticks too. The rocket, Estes green eggs. It's an egg lofter. You're supposed to put an egg in it, and you're supposed to see if you get your egg back in one piece or you have a big mess. That's the whole premise of the rocket. Okay, so the reason why I picked this has a large enough payload bay. It has a 24 millimeter engine mount, which is the D engine size. Estes is 24 millimeters. With this size engine, they have D engines, and they also have C engines. Now, in modern rocketry, the letters represent the class of engine. B is twice the power of an A, C is twice the power of a B, D is twice the power of a C, and on the way up. So this right here is actually an Aerotech composite rocket motor. This is a D22-4. 22 is the impulse power, the 4 is the ejection charge delay. So when a rocket reaches, after the engine burns, the delay, and then it blows off the top of the rocket, so the parachute hopefully gets deployed. So this rocket has parachute recovery, so it uses a parachute to hopefully land safely on the ground. And the reason why I picked this rocket is because I haven't flown it yet. I had 2 rockets with this payload configuration. One was called the Olympus, one's the Green Eggs, and I've already flown the Olympus, and I chose this because it needed to earn its wings. And it wasn't until a few days later, driving my car, I was like, oh yeah, green eggs and ham. Okay, Dr. Seuss. I just thought that was a pretty convenient, funny little little bonus. I flew the rocket with a D22-4 simply because they'll give you a little higher altitude than the Aerotech's D12 engines. Remember, 22 is a larger number than 12, so it has more power. And I also opted to use a little device, which I didn't bring, I should have brought it. It's called a Jolly Logic. It has a little altimeter built in, and it detects, you put your parachute inside it, and it wraps a rubber band. And so the rocket can blow the top off, the parachute will be held closed until set altitude, and it releases and allows the parachute to open. So reason for that is because if your parachute opens at 900 feet up there, it's going to go. You have to walk further away to get it. Now, if it opens up at 300 feet, you have less distance to walk. Unless it's really, really windy. Hey. So before taking this rocket to the launch pad, I wanted to make sure that it's going to be stable because I'm adding extra weight to the top that will affect center of gravity, center pressure. I just didn't want the rocket to, go after somebody's car or something, just instead of going, it goes, that could be bad. So this will light probably would do any damage. But I also want to see what the predicted flight parameters are. So I entered into the Open Rocket, which is an open source rocket simulation program. I selected a file for the green eggs. I entered the motor I want to use. I weighed the radio module and the battery and the frame together and entered that into the simulation. And the predicted performance of the rocket is it will be a stable flight. It's predicted that it will fly 856 feet. It will reach 7 seconds to apogee. And if you remember from the from science class, apogee is when it reaches this height, when the rocket tips over, as apogee. The ejection should happen right after apogee. If it happens before apogee, it can damage the rocket. If it happens too far after apogee, it can damage the rocket because what can happen there is parachute deploys, and all of a sudden the shock forward and the shroud lines just rip through the body tube, because of the force. You want it to happen when the rocket's kind of sort of at its slowest, and that's when it's just slowing down, reaching its highest altitude. The expected flight time is 30 seconds, and it's supposed to reach the ground at about 15 feet per second, which is a nice gentle landing. All right, the flight. I plan to fly Green Eggs and Ham on the May 31st Bright Stuff Rocketeers support rocket launch. Now, that's the reason why I wrote my article into 2 sections, part 1, part 2, because I wasn't going to have the front flight information ready for the article because the article was going to be published before, so I said, okay, I'm going to do this in 2-parter. Hey, the Right Stuff Rocketeers is a group up in Dayton area. And the advantage of using a rocket club is they have the fields, they have the rocket launch equipment, and they get the FAA waivers where needed or when needed. And in fact, the last rocket launch, 21st, was canceled because of the Dayton Air Show, and they were not able to get the waivers for some reason. So the launch was postponed to Sunday, June 1st, for better wind forecast. Never had a little conflict. I go to church Sunday morning. So I went to church. I went to lunch after church. I loaded up my car, went to church. Miraculously, the pastor kept the sermon short, and I got to lunch with about 4 hours to fly rockets. 3-4 hours to fly rockets. I just cut how many I wanted to fly in half. And here's the annoying thing: Sunday was a much windier day than Saturday. All right, so I used this 3-element Yagi to track the rocket because, the rocket's going to be moving, and I figured I'd have a better chance of getting all the packets if I was able to point the antenna directly at the rocket. And that being on a stick gives me plenty of leverage. It works pretty well. That duct tape's kind of getting loose here. Duct tape is the universal tool, by the way. Works in ham radio, works in modern rockets. The rocket flew between me and the sun, so I lost track where it was, because all I could see was, big burning ball of gas billions miles away. On the way down, the parachute got tangled. The rocket hit the ground hard. The pin broke, because remember last month I brought this and the pin was broken? payload section blew apart, but the radio module survived, and I got data. Here's the data, CSV format. I imported in Excel, and I'm giving you a little sample where it actually shows you the high altitude. You got rounding up to 720 feet, so 719.89 feet. That's close enough to 720 for me, right? So that's data. So the columns here, time in milliseconds. So I get, fine detail there. The battery power level reading, the altitude from the ground, barometric pressure reading, temperature, and notice temperature, that's wrong. And signal strength, it's actually 70 degrees, not 97.94. And signal strength. So my rocket got quite a bit of data. So the data collection was a success, but there's also some issues. Then analysis, do a little analysis on the flight profile. Simulation said the rocket was going to fly 856 feet. It actually flew 720 feet. This might be because of the windy conditions, by the way. Time to apogee, 7 seconds. It took the rocket actually 8 seconds. So the ejection charge and the simulation happened at apogee. And you can tell by the flight chart here, the injection happened at apogee, so after. Shoot deploy was set to 300 feet. It actually deployed at 400 feet. Landing, 15 feet per second was the simulation. Actuality, 53 feet per second. Way too fast. Flight time, 32 seconds. In reality, 30 seconds. And you notice another thing. The barometric pressure hits the blue line. This follows the red line. That's inverted. So as the rocket goes higher, the pressure gets lower. And you can see there's a correlation between that. And also there's a correlation with the signal strength. The higher it got further away, the less signal I had. It's pretty obvious, right? Makes sense. But did I get all the data? Well, to get an overall picture, I aggregated data on a per second basis. Remember, the data is milliseconds. Kind of hard to see what happened every second. So in this chart, you can see that I have 1 second, 2 seconds, 6 second, 8 second, 9 second. I'm missing seconds 3 to 5 and second 7. That's seconds I did not get any data. Those are the seconds I couldn't see the rocket. So what happened was, when I couldn't see the rocket, I just pointed the straight up in the air and hope I still got data. Well, I did. And it seemed to work because I actually captured the rocket reached apogee. It got it as it finished its climb, started going to climb. I also got it when the ejection charge happened. So, and you can also see in this chart that all the other seconds, I'm getting an incredible amount of data, 61, 52, 70, 64. Look at all these packets every second. Once the rocket was on its way down. Pretty compelling data, I think. Very useful data. This is all transmitted over ham radio. Awesome. Okay, data anomalies. Temperature sensor, as I mentioned, measured 97 degrees Fahrenheit rather than the actual 70 degrees Fahrenheit. And the reason for that, and this is just theory, I have no proof, and the redesign of rocket is going to test my theories, is that the clear plastic tube was creating a greenhouse effect. The sensor was directly exposed to the sun, heating it up, getting an artificial reading of 21 degrees or whatever it is, higher than it actually is. Also, if you look at the finite rocket data, you can see that the rocket on its way up failed a couple of times. Again, that doesn't happen in real life. Rockets don't magically teleport to a lower altitude and continue their flight. So there are basically two theories that I thought of. One is pressure equalization goal that I had on the payload section was too small. So the pressure differential, caused an air pocket inside the tube, and it was just reading whatever the pressure was inside the tube, not what it was outside. That could be a theory. And also, it's possible that data packets could have been corrupted, maybe. Those are two theories. I don't have proof for any of them yet, but those are what I thought of. And the next flight, I will try to prove my theories. So, what went wrong with the landing? Well, we can tell from the data that the ejection charge happened after apogee like it was supposed to. And in that chart, you can see that when it happened, it just suddenly changed direction. The rocket just suddenly accelerated in its descent, and then the parachute deployed at 400 feet. So it went, bam, boom. So when the parachute was likely pulled out of the Jolly Logic compartment, causing it to halfway open up, and which would pretty much tangle up the shroud lines. So on the rocket, when the chute actually released at 300 feet, the parachute was already messed up, and so the rocket just fell and hit the ground. And the damage was a broken fan, and the payload bay was busted open. The payload bay is held together by Scotch tape. Because without the Scotch tape, what would happen is the rocket goes upside down, and the radio slides down, free falls to the ground. That would not have been an ideal situation. And by the way, this is my favorite screen here. Kitty, the screen shows a NTSB investigator investigating a wrecked rocket on the ground. So, and the rocket looks like my green eggs too. I can pull that slide. Okay, so here's the damaged rocket with the broken fin, and you can see that it got repaired. And here it is, repaired, proudly displayed with a modified payload section. And the rocket next to it is going to be its successor after it finishes the Green Egg and Ham project. This rocket here is a two-stager and also has much larger motors. So that thing will go higher. And the reason why I want to go higher is because I want to see what happens with the data signal strength as the rocket goes higher. Will I be able to still maintain contact with the rocket when it's at 1,500 feet, 2,000 feet? I think I can, but now we'll find out. So the next on the next slide, the rocket's been repaired. The payload section has been modified. I replaced the plastic tube with a cardboard tube, painted it white for reflecting solar energy. Then I cut two little square holes for airflow and also pressure equalization. This will, in theory, keep the temperature sensor cooler and also allow the pressure to remain equal to what it is outside. That's what around it went to. Notice I have my call sign on the side of the rocket. Okay. That's not a toilet paper roll. That's actually an official rocket. Official rocket. Yeah. So I also plan to use two receivers. One hook to be using on the Yagi, but I also plan to set up a vertical, 5/8 vertical antenna that's fixed. And that will allow me to do a data comparison of what did I catch on the Yagi and what did I catch on a vertical. Do a little experiment to see what the differences are. Will the vertical be able to still pick up the rocket when it's 800 feet up in the air? Don't know. It'll be fun to find out. And also, the next flight, I'm going to use the same motor configuration, so I will have similar flight profile as the last time. If I use a more powerful motor or less powerful motor, it's going to be the same, same scenario. Okay, what's next? Well, I want to add data logging. I want to log to an SD card so that I can compare true data to what I've actually received. So I actually have, okay, the rocket recorded this information, saved to a file, and then I can actually compare it, see if anything changed, see if I'm missing anything, see if data got corrupt. That will prove or disprove the data corruption theory, right? And there's no need to transmit massive amounts of data like more advanced sensors like the accelerometers. That's a lot of data. I mean, there's no reason to really transmit all that. You just transmit what's necessary and store all the other stuff that's nice to have. In the accelerometer data, there's a lot of data, and that will just take up cycles. More sensors, accelerometer is to measure G-forces. So you can actually determine, how much thrust is the rocket is going through. When it actually deploys, when it hits the, what forces are. I also want to add the gyroscopes to report X, Y, and Z positions of the rocket. That way, you can enter that into a game engine, like Unity, and you can actually build a 3D simulation of your rocket's flight. That'd be pretty cool, don't you think? So, I've actually seen people do this on the internet. I'm not inventing anything here. I just do it on my own. GPS tracking, transmit rocket's location in real time till it lands in the bush. And I know once it lands in the bush, you don't necessarily GPS can, okay, be within a 15-foot area, you know, which push, that's poison ivy. Do I really want to, okay, ARDS begins for when you lose telemetry. I mean, the GPS modules can fail. The rocket can go below the horizon and stop transmitting the data, you know, whatever, you know, you have a hill in the way or something. So the ARDS begins. What poison ivy patch did my rocket land in? Okay, and then you have somebody else's kid go grab the rocket for you. Handheld receiver. I want to build a receiver with one of these that has an LCD that shows me the rocket's altitude and its longitude and its location. Maybe even show me what direction it is. That way I don't have to look the laptop along. It's recording the data and it's showing me information. That's the last thing I do. That's probably the most complex thing, but it'd be really cool. That'd be the coolest kid at the rocket launch with this little handheld computer thing. It's a learning experience too. I've never built anything like that. And this is all culminating to bigger, higher flying rockets. High power rocketry means higher altitudes, which means it's harder to track the rockets, which means it's easier to lose. And, you know, bigger rockets cost more money, a lot more money. I like to get them back. Okay. All right. Why build when you can buy? Well, this is a fun learning experience. I don't know much about Arduinos. I know some. I don't know, much about rocketry. I know some. I'm learning to program the Arduino. I'm learning, about the physics and the data and how to analyze the data. This is all new to me. And some problem solving and troubleshooting. I ran into problems with the sensor. Why is it unstable? Satisfaction of engineering custom solutions. Okay, I need to figure out how I'm going to put the electronics in my rocket. Well, I have some spare balsa wood. I could build a frame out of that. I could also 3D print something probably because I have a 3D printer. And stuff like that. So engineering, cross pollination between technical communities. Share ideas among rocketeers. Share ideas among ham radio folk. Some people say, hey, use this kind of antenna instead of that kind of antenna. Or have you thought about using this particular radio or something? And, because you show up to a ham radio meet with a rocket and you get some interest, and you show up to a rocket meet with a ham radio rocket, that's going to get some interest too. And also, this embodies the immature radio experimentation spirit. The hams are experimenters. We like to tinker and play with things and sometimes break things. But all right, any questions? You bet.
What's the typical distance from launch to how far away?
How far away the rocket goes depends on how windy it is. If it's a very windy day, it's going to go far. It also depends on how high it is and how high the parachute deploys, or what kind of recovery system you have. So you can have the streamer where the rocket will fall relatively launch pad. And then on a very windy day, your rocket go 1,000 feet. You could be walking, half a mile to go pick up your rocket. So some of the people that fly the high power stuff out in the desert, they can go miles, like 10 miles to get their rocket because that's how far it drifted. Which is one of the reasons why having a recovery system that controls the parachute from opening until you get to a lower altitude is such a good thing. Because if you have a parachute that opens at 20,000 feet, better hope you have a vehicle to take you the distances because it's going to go a long way.
When you launch, what ignites it? Like it's a start.
It's electric igniter. According to the National Association of Rocketry Safety Rules, and the rocket launch is a NAR rocket launch, you have to use electric igniters. You're not allowed to use the light fuses. Yeah. So the electric fuses are much safer, and they won't say they're more reliable, but it just allows you to be away from the rocket when it goes off, because sometimes they blow up on the pad. I had one happen on the last launch. A brand new night smoke rocket. First launch, kablooey. The rocket engine turned into a dynamite stick, basically. So, yes, Estes replaced the rocket and the rocket engine adapter and the rocket motors in their warranty. Any other questions?
I got a few. So with your modified payload compartment, you get those vents in it.
Mhm.
Will that affect your parachute ejection at all?
No, because that's a good question. The parachute is actually below this bulkhead. So there's a bulkhead here. So the module is inside here, and I also have an additional bulkhead just in case any gases. I have a piece of tape stuck in the hole.
Okay.
So it is separate.
So your payload actually it ejects with your nose cone. Yeah. Okay.
Yep, and everything's tied together. It's a good question. You know,
All right. Yeah. Second question. So with your antenna experiment that you're thinking about doing with the vertical, have you thought about, so with the vertical, you're going to have that null off the top of it. So have you thought about, since you're using what, like 433 or
433 megahertz.
yeah. Have you thought about going dipole so that you don't have the null off the top instead?
I haven't thought of that. See, this is why you bring these experiments to an AM radio club. That's a good idea.
Might give you better coverage vertically, maybe.
We use vertical sideways.
Bring
Yeah.
the vertical sideways. That's an excellent idea.
Any other questions online? You're welcome to speak up. Nick,
The engines, how much do those run?
Okay,
They're
well-
single use, right?
Yeah, these are signal use. This one's about $7. It's a D, so it comes in a 2-pack. So the cheaper engines you get like 3 for maybe $7. The bigger ones, this one is $7 for each, so it's 2-pack. One of my rockets, the Mirage, it's a 7-foot 1-inch rocket. That flew with a G79-7. That was a $40 rocket motor. And I plan in the fall, when I get my level 1 certification, to stick in a H motor, and that's a $50 rocket motor. That's single use. So when I fly that rocket, it's literally $50 up in smoke.
How high will that go?
What was that?
How high will that 2,000 go?
Well, it depends on what rocket you put in, but the Mirage is a huge rocket. It's taller than me, so it's pretty heavy. With the H motor on that one, it would take it at about 1,500 feet. Okay, if you put that in a small rocket that's this big, that'd probably go 2,000 or 3,000 feet.
What material?
Depends what kind. The Estes motors are all black powder. This one is a composite ammonium perchloride. It's aluminum powder with ammonium perchloride oxidizer. But different rock motors have different formulas that can have different effects. They have Blue Thunder motors that have different chemical. They have sparking motors that actually produce sparks out, which means you have to have fire extinguishing equipment because you always set the ground on fire when you set one of those things off. But the different rock motors are made out of different things. But all the Estes stuff is black powder, and most of the low and mid powered stuff is ammonium chloride, or some variations of that formula. Good question.
And every next to him, if whatever happened, lost everything. What's the best with lost? So
The rocket's about $17 at Hobby Lobby. The radio module is $25. The battery is like $7. The temperature sensor is like $10 to $12. So $50, $60 maybe.
chances of not getting it back probably pretty slim.
Pretty slim on this size rocket because it's not going to get really high enough to really be a problem unless you put an E motor in or an F motor. Then you'll never see it again probably. So I think this is a very small, and I intentionally started with a small rocket, and I'm going to be incrementing my way up. So, less expensive, more expensive, more expensive. This project is going to $10, $25 myself to death if I'm not too careful. You got questions?
I had 2 other questions, but I don't know if I remember them now.
Okay. All right,
Jordan, does this just use a little button cell battery for the outdoor?
No, I use a lithium ion. So I purchase little, which means you don't want this to get damaged because it won't be the only thing that's producing smoke.
All right, I remember one of my, oh, go ahead.
I think it's sort of alluded something that I wasn't sure I understood. You have a rating or some sort of training program that you're supposed to go through to be able to get involved in rocketry or?
Okay, that's a good question. anything above, below G impulse, you don't need any certifications whatsoever. So anybody can buy, unless you're going to be 18. But A through D, a teenager can buy. D and E's and G's is considered bid power. Don't need certification. You have to be 18 plus. Then the high powered is broken between H and up. And those go from $50 motors to $8,000 motors. Those levels of certification are broken up into 3 different certifications. And the technical, and just like ham radio exams, the level of technical knowledge increases as you step into each level. The level 1 is just a basic rocket that has a higher power rocket. Level 2, you have to have electronics for dual deploy systems. And level 3, you have to have even more complex electronics and stuff. Because, the bigger the rockets are, the less safe they are. You got to make sure that rocket is going to go where it's going to go. And when it lands, it's not going to fall and go through somebody's house. Or you got to make sure it's not going to hit an airplane or something. That thing hits an airplane, it's lined up, it's not going to do any damage. But if it's above, 5 pounds or something like that, that's a serious problem.
Can you guide those things while they're going up, or is it just?
Well, if you want to go to prison.
Huh?
You're not allowed to make a guided rocket. That's a missile. I mean, there are some people that do, but they're really in the gray area, and they don't publish exactly how they do it on YouTube because they will have 3-letter agencies knocking on their door real quick.
Oh my.
Because you get into a rocket that's guided is considered a missile. Okay, you can see why there could be an issue with that. And then you publish how to build these things, and in some countries that might not be very friendly towards us, it's, hey, this is how you build a missile. So very, very gray. People who do it, they're very wary about sharing how they do it.
So similar to Mick's question, you mentioned FAA waivers. Where do those kick in at?
Well, certain altitudes. So when we fly in Cedarville, we have a waiver to go to like 20,000 feet, okay, which does go into commercial traffic. And those rockets are heavy enough to pose a threat to airliners. The Dayton area, Heber Heights, we fly rockets that don't normally require waivers, so less than G impulse and less than 3 pounds, I think it is. And but because of the Dayton Air Show, a waiver would have been needed, and they said no. So,
but it's based on altitude, weight, power. Okay.
Yeah.
Okay. Any other questions?
The drone limit is 400 feet
Mm-hmm.
on ground level. What, when do you have to start, at what altitude do you need waivers?
Depends on where you are,
Well, yeah,
how close you are to an airport. If you're out in the middle of, the Nevada desert, space. Okay. If you're in Cincinnati, you're not flying rockets. You're in CVG in London. You can't. You go into. They have rules that say you can't fly rockets in the parks because it scares the birds. That's not the reason. I mean, you look up and you can read the serial number on the jets as they come into the CVG.
Any other questions? Anybody online? Speak up if you have a question online.
All right, did you have any more questions?
I think I'm out.
Okay.
All right, I'm just checking the chat. A couple people said good presentation.
Thank you. Now, keep in mind, I did this presentation all in one day, put it together, because I was asked on Saturday. And since it's field day, I didn't exactly have time Saturday and Sunday to work on it. So,
yeah, you still did a great job.
yeah. And also, I do want to put a little plug. June and July, Q-Fibers have the article that this presentation is based off of. So part 1 is the construction of the radio module. Part 2 is the flight and analyzing the data. I think I did a really good job writing it. It was a lot of fun. Took me a while to compile all that data and put it into readable format.
Part threes yet to come.
There isn't a planned part three. There may be something in the future when I get to adding, ARDF. Because I think the rest of it is just rocketry stuff. And until I start incorporating more amateur radio, I'm probably not going to do another article until I get into, more ham radio specific. But I do plan to rewrite my article in a rocketry point of view and submit it to the Sport Rocketry magazine. Take out the rocket stuff. I loaded the rocket motor, just rocket motors. The 22 means it's 20. The Rocketeers will know that. Well, I'm going to replace that with amateur radio is a service and blah, blah, blah. Just rework it to a different audience. So I do plan to do that. Just rework the article and submit it to Sport Rocketry. And that way I get, double bang for the buck. Not that I get paid for the article or anything. But I think it's an interesting enough topic that the people on the other side of the aisle would appreciate it.
Any other questions?
No?
All right, thank you, George.